Hello, my name is Tovio Roberts, and we're going to explore some counting, some simple counting using different base systems and using arbitrary symbolic numeric systems. So I've got this repo up at GitHub/clownfragment/brief introduction to counting, and I'm going to put that in the chat. It should also be in the description. And we're going to, kind of get into this. So counting kind of comes up a lot, and we're going to think about this in a kind of straightforward way. So let's look at kind of an abstract idea of what counting is. So the first thing we're going to count in is decimal, which we all probably know how to do. Except now, instead of just writing the number 1, I'm going to write a 0 in front of it, okay? So I'm going to do 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7, 0, 8, 0, 9. And what happens here is that the 9 rolls back to 0, and the 0 rolls to 1. And we go 1, 1, right? Etc. And, eventually we get to 9, 9. Now, this may seem like, oh, why are you showing me this? I'm showing you this because we can think of counting in any number of bases, right? This is base 10. But let's consider binary, right? So binary, 0, 1, 1, 0, 1, 1. Oh, I'm sorry, there's a 0, 0 up there. 0, 0, 0, 1, 1, 0, 1, 1. There's also a 0, 0 up here above base 10. So when we think about this, let's say we want to do, this is 2 bits of binary, or 2 numbers of binary, right? But what if we want to do 4-bit? Well, we do this, right? And if you're familiar with kind of computer organization, you're going to know that underlying processes in a machine things are stored this way. Things are stored this way in memory, stored this way on hard disks. They are, procedures are written as strings of binary. So, this is a kind of, we've got a maximum here of 1, 1, 1, 1. And this, when it rolls over, it actually rolls over like this. But if we have it constrained to 4 bits, this is all that we care about. And in the underlying mechanisms of your computer, something needs to be done with this 1. Often it's destroyed, or it gets carried into a new place where it's stored. So that's binary, but we're not really talking about binary in and of itself. We're not really talking about base 10 in and of itself. Let's think about base 3. So base 3, let's do 3 numbers of base 3. I sometimes call these trits, T-R-I-T-S. I don't know if that's, I'm sure there's a better word out there, a real word. So 0, 0, 0, 0, 0, 1, 0, 0, 2, 0, 1, 0, 0, 1, 1, 0, 1, 2, 0, 2, 0, and on. So, these are numbers, but let's consider a different system that uses something a little different. Let's think of a list of words. We'll have dog, cat, and bear. And let's consider dog to be something like 0, cat to be something like 1, and bear to be something like 2. Okay? And we can start thinking about this a little bit in terms of Python, and that's going to be helpful later. So 0 is going to be equivalent to, let's say, dog, dog, And 1 is going to be dog, cat. 2 is going to be dog, bear. 3 is going to be cat, dog. And you can kind of see here that what we're looking at is very much like that trinary, right? So 0, 0, 0, 1, 1, 0, 2, that is, and 1, 0. And we can continue that on. So this is just to kind of give a foundation to think about some of this. And I'm going to take it a little bit further. And I'm going to do this in light of binary. So I'm just going to count in binary let's do 4-bit binary. So I'm going to build a distribution of the sums of the bits. And I'm doing this in part because with binary, as you might know, or you might not be aware, we can model a binomial process this way, where zeros are failures and ones are successes, and we can consider this to be 1 success out of 4 trials, 2 successes out of 4 trials, 3 successes out of 4 trials, and we can actually use binary as a means to distinguish some sort of trial-based probabilistic mechanism, right? So 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. And if we count these zeros, we can start building a distribution. So there's one instance that has 0 ones. Sorry, counting the ones, not the zeros. So this is this instance, right? If the sum of these bits is 0, and it is in one instance, then we only count that once. Now let's count the sum of ones that are 1, right? So we've got 1 here, and 2, 3, 4, and that looks like it. 2, so 1, 2, so 1, 2, 3, 4, 5, 5, and then 3, 1, 2, 3. Actually, I think 2 should have 6. It does have 6. I missed 1. Okay, so 3. We got 1, 2, 3, 4. And then 4, there's only 1 instance. And if you think about this, this looks kind of like this, right? So this is actually a binomial distribution with 4 trials, right? And this is going to inform some of the other things that we do later. So I just wanted to, if you haven't seen this before, this approach to using binary to discern binary counting to discern a binomial distribution, this will be informative for later. Okay. All right, so let's get to coding. And we're going to, I'm going to work out of this repository here. And I posted that link. So feel free. And I'm going to just start off coding a really simple way of making binary. And I'm going to make a file in here called, let's just call it counting.py. And I'm going to open this. Actually, I'm just going to run VS Code here. It's going to give me a million pop-ups because they're helpful, apparently. And here's our file. So the first thing I'm going to do here is I'm going to count in, well, let's say I'm going to count in binary. So I'm going to say, here we are, so binary, And let's just do 0 and 1. And the order of these matter, right? So if I did 1, 0, that would be a little bit, it would end up giving us a count that was sort of out of order. And the way that I'm going to do this, I'm going to say for bit in binary. And this is going to be, let's say this is, actually, I'm just going to use letters, so I type a little less. I'm going to make 4-bit binary here. So for I, J, K, and L. And I'm just going to print these out. I'm going to say print, and I'm going to do I, J, K, L. I, J, K, and L. And if you notice what happens here, this for loop is going to run twice for every time this one runs, which is going to run twice for every time this one runs, which is going to run twice for every time this one runs. And notice that this is just going to sort of cascade in and out. And as it turns out, this is going to print out some binary. So let me just run this. So Python counting.py, and there we have some binary, right? All zeros, 1, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, etc. So notice all we have to do to add, to make this a base 3 system is, well, I'm not going to put 3 in there. I'm going to put a 2 in there because that would be a base 3 system. And this is going to give us that trinary. It's going to give us four places of trinary. So 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, 1, 0, 0, 0, 1, 1, etc., right? And you know, let's take that example. Oof, I don't know what's happening with my bash. Let's just do that. Wow. Go ahead and terminate that. Not sure what's happening there. So what we can do here is we can say dog bear and cat. And this is sort of like a 0, 1, 2 scenario. All right. So hopefully that doesn't happen again. And when we do that, we get these outputs, right? So dog, 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 bear, dog, 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 cat, dog, dog, bear, dog. And this is a base 3 system with arbitrary symbols for numbers. So that hopefully is kind of informative of where we're going with this. And this will probably look a little nicer if I did something like that. So yeah, this code here is, well, let me say this. This code here is really kind of stiff, right? Like if I want to add another layer of this, you know, I have to put in another nested for loop. And this kind of code, I think most people would say, like, what if we had 10 places that we're trying to do? This kind of code is not flexible enough to give us 3 places and then 10 places. It's pretty stiff as it is. So, you know, I would have to keep adding for loops and taking for loops away in order to do that. Luckily, there's kind of a nice way to go about this. And I'm going to do this through the lens of doing a decimal conversion. And first, I'm going to do a decimal conversion to binary, just to kind of give an idea of this that hopefully will be, you know, lend itself to algorithmic thinking. So I'm going to just push this I'm just going to call this for loops. And I'm going to go back to the document camera and describe this algorithm. So let's say we have some binary. This is going to be, I think, pretty straightforward. So let's say we have some binary. Let's go 0, 1, 0, 1. A way that we can think about this is that this is the ones place, right? And so this is 1 times 1 plus, 0 times 2 plus 1 times 4 plus 0 times 8. And these, of course, go away. And we've got 1 plus 4, which is 5. And it turns out that the decimal value 5 can be represented in binary by 0, 1, 0, 1. So this, just to sort of restate this, 0, 1, 0, 1, this is the ones place. This is the twos place, right? Ones, twos. This is the fours place. And this is the eights place. So hopefully that makes sense. Now, this same construct applies to really any language, or sorry, any numeric system. So if you have a base 10 system, so let's say we have 5, 9, 3. This is the ones place. This is the tens place. This is the hundreds place, right? So this is familiar. This is a little less familiar because we don't use binary all the time. We do use decimal all the time. We can see this is 593. We can see that this is 500s, right? So what's happening here? It's a base 10 system. So we multiply by 10. We multiply that by 10. And then out here, we have the thousands place, right? So there are 3 thousands, 500s, 9 tens, and 3 ones. So that's pretty intuitive, I think. Let's think about a base 3 system and say 0, 1, 2. All right. Or let's do this. Let's do 2, 1, 2 in base 3. So there are 2 ones. There's 1, 3. And there's 2 nines. So this is 2 plus 3 plus 18, right? So that's 21, 23. And we can take this process and sort of reverse it. So let's think about how we might reverse this. Let's say we have a number in binary. And actually, let's say we have a number in decimal and think about converting it to binary. So let's do the number 23. So with 23, we can, if we're trying to convert this to another base, we can simply take the division and modulus of this number. So, this is decimal, this is binary, and we can take 23 and divide it by 2 and figure out what the remainder is of this, okay? So 23 divided by 2, first off, this is going to be 11, right? And there's a remainder of 1. Does that make sense? So we've got a remainder of 1. 2 times 11 is 22. Then we divide this by 2 again. And so it goes in 5 times with a remainder of 1. And we can do this by 2 again. And it goes in 2 times with a remainder of 1. and this goes in one time with a remainder of 0. And when we look at this, we can construct a value. Okay, so when we think about this, there are how many ones, right? Oh, I'm sorry. We need another 1 here. So, okay. So we've got, yeah. Sorry, 1 sec. Check something. And so when we're looking at this, we sort of rewrite this and say 1, 0, 1, 1, 1. Then we can convert back, right? This is, we've got 1, 1. We've got 1, 2. We've got 1, 4. We've got 0, 8s, and we've got a 16. So this is 16 plus 4 plus 2 plus 1, and that's 22, 23. So we can see that we can convert back and forth using this algorithm. This will work for any number system, but let's go ahead and look at this in using binary first. Okay. So I'm going to go ahead and delete this. And let's write a function called decimal to binary. And we'll put in a decimal number. And let's consider a number of places. So let's do number of places. And we'll set this to, well, let's set it to 4. Let's just set it to 4 to start. And I'm going to return the binary in a list. So let's just go ahead and write this. I'm going to say for whatever in range the number of places, the place is going to get, well, I'm going to modify this decimal number. So I'm going to just say x gets dec. And I'm going to say the place is going to get x modulo the base, which is 2. And then I'm going to append that place. And then I'm going to floor divide by 2. Okay, and that's just going to get rid of my my decimal place. And as x goes through, we're going to end up with a 4-bit number representation. Now, there are ways that this won't work, and I will sort of try to demonstrate that. So the last thing I'm going to do is reverse that list, and we're going to get a representation that we're going to get a representation of this in a reverse list form, so that it should be in the right order. If you notice, what happens here is we're dealing with the largest number first, and so we're appending the largest place last. Okay. So if I'm just going to print this, let's do dec to binary, and I'm going to put in the number 23, and I'm going to set number of places to 5. And what this should show us is 10111, if I don't have a mistake in here. So let's do Python counting 10111. Okay. So that's doing what we would expect it to do. Now let's code this a little further. And let's make a counter, right? Let's get all the places for a certain range of decimal. And that kind of makes sense. So we're going to go from, you know, however many 0 bits, right? Like 0000 up until some high value of, you know, 1111, right? And this is going to be pretty straightforward. Let's say, let's call this get binary in range. And let's do number of places. And I'm going to set that to 8, not 80. Let's do 8. And I'm going to make a relation between some decimal and some binary. Let's see. All right. So this is pretty straightforward for I in range. And I'm going to go from whatever, from 0 up until n places. So this is going to be 2 to the number of places. And hopefully that makes sense why that is, right? Since we're doubling, we start with the ones place and then we're doubling every time. So we're covering all numbers up to 2 to the 8. 2 to the 8 in this case. If we set it to a different number of places, it would be 2 to that number of places. And so I'm just going to call out to the decimal to binary to populate this counts dictionary. So counts dictionary sub I is going to get decimal to binary of that decimal place with the number of places. So it's going to be I and then the number of places that we have right here. And then I can just return the counts dictionary. And I'm going to go ahead and put in an if main block here. If name equals main, then we're going to execute whatever's below this. And that's just to sort of separate our code from our procedure, our functions from our procedure. So I'm going to say for key and value and get binary in range. And let's do the number of places to be, let's just do 4 to start with. I'm going to print the key and the value. All right, so let's see how that goes. There, let's see, int object is not iterable. Well, that makes sense because I did not put dot items, which is probably my most common error in Python. Okay, so notice we have a relation for all values between all values of decimal between 0 and 15. And notice 15 is 1111. If I do 8 places, then we go up to 255. And that number might be familiar if you do graphic design work, right? That has everything to do with the storage of colors, right? 255, 255, 255 is 111111, which 11, which is the color white, right? It's a full saturation of color. So hopefully that makes sense. So, you know, I mentioned making this work for an arbitrary base. So why don't we think about how to do that? That's kind of, let's say, an arbitrary number of values in the base, right? So we could have a base 16, or we could have a base 30, we could have a base 4, base 5. It turns out this is pretty easy to do. We can do something like this. We can set a base, And we can say for, so we're still going to put in a decimal value to get the base out. And we're going to stick with this paradigm, even though it's a little limiting because we always have to pass through decimal in order to solve things. But, you know, we use decimal, and I think decimal is pretty intuitive. So we'll stick with it. There are definitely other ways to go about doing this, but for now, we're going to do it like this. Okay. So I'm going to say for whatever in range, the number of places, the place is going to get modulo by the base. And we're going to append the place, and we're then going to divide by the base. And so that's one thing we can do. And to kind of demonstrate that this is working in a way that we'd expect. Oh, let me change this to from decimal to, let's say, base x. So that's just whatever base that we're converting to. Let's test that, see if that works. So decimal to base x. And let's think about converting the number 76 into a base 7 system with a number of places of 10. So we might expect there to be a lot of zeros when we run this. Let's just see if it works. Oh, probably need to print that. Okay, so there are 6 1s, 3 7s, and 149. So that's 49 plus 21, which is 70, plus 6, which is 76. So that looks like it's working. And the next thing we're going to do is modify the get binary in range to get a range for arbitrary bases. So let's do that. So instead of get binary in range, let's do get, let's get a count from the base. So I'm just going to call this get base count. And we'll stick with the number of places as being 8. And we'll say for I in range 0 to, oh, well, we need a base in there, don't we? So let's do, yeah, let's just call that base. And let's put the base in here. And we'll say for I in range from the base to the n places. And this is going to take the, oh, that's the decimal number, which is I, the base, and the number of places. So I believe that looks good. Let's go ahead and run this loop and say we need to put in the base, and let's stick with this base 7 and see how that goes. Oh. This is Python counting. Oh, name get binary in range. That's not the name anymore. I will rename this to get base count. Okay, name dec to binary is not defined. Well, that makes sense because I changed that. Just grab that. Let's see. This is going to take a little bit because we're doing 8 places of base 7. Why don't we clean this up? Why don't we make this a little bit nicer and just do 4? Okay. So this is a base 7 system. And, we can look at this and we could do something like, well, there's 4 1s, 5 7s, 4 49s, and then, oh gosh, not sure what the next is, but, we could add those up and we can see that this is working. So, where can we go from here? There is something that we can do that I alluded to earlier. And we'll start off by doing this with binary. And I'm just going to, I'll start off kind of recreating what we did before. And so here we've got this, I'll just run that again. Here we've got this counting in binary base 4. Now, what if we want to, well, let's say we want to get a distribution of this. So why don't we do that? Why don't we write the distribution of sums? So we'll relate this first to binomial in the way that we already did. And this is going to take a base, and we'll set the number of places to 8 offhand. And we'll leave it at that for the moment. And let's say that the base count is going to be this. It's going to be just the count, right? And that's going from 0 to our maximum number for the number of places that we have. So this is going to be get base count, and we're going to put in the base and the number of places. And so that makes available to us this count over here, right? We've got this dictionary where we've got the decimal value related to the symbolic representation for that decimal value. And we're also going to fill a new distribution. And this is going to be a distribution of sums. So I'm going to say for whatever and number in the base count dot items, I'm going to make a digit sum. And this digit sum is going to be the sum of the number that we're getting out. And we're then going to ask if the digit sum is not in the distribution, then let's put it in there. And let's say distribution sub digit sum. We'll set it to 0. And then in every case, we're going to set this, we're going to increment this. So this is the syntax I usually use. But you know what, for this time, in case that's not a syntax you're used to, I'll just set the digit sum to 1, and then I'll do an else in there. So it's just checking if the digit sum's not in the distribution, and if it is in there, it increments it by 1. If it's not in there, it puts it in there. And then at the end of this, we can just return the distribution. So in this case, let's go ahead and grab this, and this is going to be a representation of the binomial distribution. So we're going to get the distribution with a base of 2. We'll do 8 places, and we're going to print the k value, which is the sum of that binary, and the v, which is the count of the occurrence of that sum. So what? Oh, I didn't save it. Oh, let's see. What's going on there? I am missing for whatever in base count.items. Oh, I'm just missing a colon. Okay. And that should be pretty straightforward, I think. So 1, 8, 28, 56, 70, 56, 28, 8, 1. The largest value that we can have is all ones, which is, 8 ones is 8. And that only occurs one time. The lowest value is all zeros. That can only occur one time. And everything else is somewhere in between. So, let's look at this for a base 3 system and see what we get. So naturally, these numbers can be larger, right? Because if we have all 2s in 8 places, right, that gives us a maximum value of 16, and that occurs one time. 0 again occurs one time. So we could do this for some arbitrary system, and let's say we have a base 64 system, and I'm only going to give this 4 places because it's going to take a little bit for it to run fully. So you can imagine what this is doing if we displayed this, and maybe I will display it. Let's see, just so we have kind of a nice visualization of this somewhere. We'll just print this list in reverse like this. And maybe I tried to give it too large a number. So I'll do 3 places of 64. Yeah, and still, this is going to take a little bit of time, but we'll get a clear idea of what's happening here, right? And this is a base 64 numeric system that we're seeing. And then out of the other side of this, we're going to see the distribution that we get. And, this is a lot of numbers. But this is a distribution of these sums that we're getting out of the other side. Okay. So this works for a sort of standard numeric system. It doesn't work for that kind of arbitrary numeric system that I described before, the dog, cat, bear system. And let's go ahead and write some of this so that it works for an arbitrary system, such as, let's call this system, let's call this numeric system, and we'll set this to dog, cat, bear. And let's write kind of another function in here that that will allow us to utilize this decimal to base x function, and it'll allow us to kind of insert symbolic representations. So I'm going to just call this dec to symbolic, and we're going to put in a decimal number, and then we're going to put in a numeric system, and we're again going to put in a number of places. Okay. And let's make a little note here that our symbolic system has the leftmost item in the list as equivalent to 0. Okay. So that means that in this system, this numeric system here, dog is the 0th index, and it's also a representation of the number 0. And making cat 1 and bear 2. All right, so we're going to get a number representation of our decimal number, and then we're going to convert that to the value in the numeric system. So the number representation is fairly easy to get. That's going to be just decimal to base x, right? We're just utilizing this function with this decimal value. And we're going to, so we're going to give it the decimal value. And we're going to give it a base. And how do we know the base? Well, the base is just going to be the length of the numeric system. And, I have to make clear here that this is a very simple numeric system where we have a one-to-one correspondence between a symbol and a counting number starting at 0 and going by ones. So we're not really thinking of this as a more complex numbering system that, skips counts or anything like that. It's just going to be as simple as any single base system. So I'm just going to set the base to the length of the numeric system, and I'm going to set the number of places to the number of places. And that's going to do most of the work for us. And then we're going to return something. What we're going to return is going to be the indices for each value in the number representation, right? Remember, this is a list, and we get a one-to-one correspondence between this list and values in the numeric system, so we can just use it directly. So numeric system of x for x in the number being represented. All right, so we've got this, and we can utilize this. So we've got a numeric system we can pass in, and we're dealing with essentially trinary, so I'm going to do 8 places in this. I'll just do 5. There's no reason to do more than that. And the numeric system is going to be this dog, bear, cat, and the decimal value, let's do 32. And I'll go ahead and print that. And let's see what we get. So we're printing a couple things here. We're printing, remember, in that original function, we left a print statement in there. So 0 is dog, 1 is cat, 0 is dog, 1 is cat, 2 is bear. Dog, cat, bear is our number through an arbitrary numbering system. So that is pretty straightforward, I think. If you have any questions about that, please ask. I don't know if, this is sort of, you might be asking, why would you do something like this? And there are reasons that you might use an arbitrary number system. You might be working with some kind of in-series encoding for various parts, or for some kind of data storage. It could be something to that effect. You might be making, you might be utilizing some sort of subtle, or simple encryption of a number system. That could be the case. I think more often than anything, you might approach this through finding permutations and combinations, and we're going to do sort of a brute force permutations and brute force combinations at the end of this. So let's look at making this work with our other functions. So we've got this decimal to symbolic, and now we need to modify our get base count. So if we want to be able to count in this arbitrary number system, we're going to have to do a little bit of work, but not much, in order to utilize this toSymbolic function. So we've got for I in range, and we're going from 0 to the base to n places. So in this case, we can just go from 0 to the length of the numeric system that we are going to pass in. So the length of the numeric system, which is indicative of the base. So we can just change base to numeric system and counts, the counts dictionary sub I. Instead of dec to base, we're going to do dec to symbolic. And we're going to do I, and we're going to pass in the numeric system. So that should actually do it. And let's sort of just count in this system now and see what that looks like. Okay, so this is printing a specific number, the version of 23, but let's go ahead and count in this numeric system. And I'll go ahead and sync this first. Okay. So let's go ahead and run Python counting.py. And the thing is, this is sort of hard to read, so I'm just going to say for k be in this dot items, and I'll just print. I'll print the k and the v as I did before. Oh, I could have just used a little bit of this code up here, but that's okay. Oh. For kv and get base count numeric system. Oh, I have an extra parenthesis. Okay. Okay. So these are the decimal equivalents to the numbers here, and maybe just for this, let's just do 3 places, and I think that might be a little bit more readable. So here's our symbolic to decimal conversion. Dog 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 is 0, dog dog cat is 1, dog dog bear is 2, dog cat dog is 3, and so on. Okay, so I'm gonna clean that up a little. I'll leave that in there. Okay. So that appears to be working. And now let's modify some other things. Let's get a distribution of these items. And it may be, I don't know, it might be a little funny to think about this, but we're going to go ahead and do it because I think we want to get a distribution of the sums of some system like dog, cat, bear, okay, which is a base 3 system. But let's think about this in terms of sums of the symbolic values. So I'm going to set this symbolic. We're going to assume a symbolic system. And this, when we get the base count, we're going to pass in a numeric system now, right? That's what we've changed to. So the base count is going to get the base count of a numeric system. And we've got this distribution. And we're keeping this essentially the same, but instead of just summing the digit sum here, we're going to go ahead and we're going to get a digit sum using a separate function. And we're going to pass in the numeric system. We're going to pass in the number. And we're going to pass in this values for symbolic, which will give us an option of switching between a decimal and symbolic representation. And then the next thing we're going to do, if digit sum is not in the distribution, distribution subdigit sum, I think that's everything for that function. And we just need to write this get digit sum function. All right, so get digit sum of, it's going to be a numeric system, passing in a number, and we're passing in whether or not we want it to be symbolic. And we're going to make a list here, and this is going to help us in building a digit sum. So we're going to say for each item in the number, and remember, number is a list and it contains a number of elements, right? We're going to say digit sum, the decimal version, dot append, and we're just going to append the index from that item. Remember, the index, it correlates directly or is tied directly to the numeric value for that symbol. Dog is 0, right? It's the 0th item. And then we're going to say if symbolic is false. We could just say if not symbolic, but I'm just going to be really clear here in the way I write this. We're going to return the sum of those values, those index values. And that should be pretty straightforward. We're just summing and getting a decimal value out at the end of this, if we don't want to have a symbolic representation. And otherwise, and notice we're returning here. I could put an else here, but I don't need to. So if the digit sum symbolic, otherwise we're going to convert from the decimal value to the symbolic value, which is going to give us a list. And we're going to convert by the digit sum, the sum in that digit sum decimal list. And we're passing in that number, we're passing in the numeric system, and we're passing in the number of places, which is the length of that digit sum in its decimal form. So we can then, this is just a little bit of error checking. We're going to make sure that everything in this is a string in case we have a mixed list where some things are not strings, because we are going to make keys for a dictionary. And to do that, we need to use join, which requires that everything being joined is a string. So digit sum symbolic, we're just stringifying everything. And when we return this, we're going to return this dot join the digit sum symbolic, and we can see if that works. Let's get a base X distribution and see where we have some errors. All right. So something I just noticed in get base X distribution, we're no longer passing in a base, we're passing in a numeric system. So we need to change that. I think everything else is fine. Okay. So we're going to pass in numeric system. And number of places, let's do 4. Symbolic, let's keep symbolic true. So I'm going to say for k, I'm just going to grab some code that is already here. For kv and get base x distribution. And let's do, let's just grab this up here for, we're just printing out the key and the value. And I think we'll see if there are any. Okay. What are we seeing? Get digit sum, numeric system, number, symbolic. Okay. This is missing. It's def. Okay. Okay, too many values to unpack on line 73. That's because I didn't use dot items, which is, again, my very common error. And there we have it, which is, this is sort of funny. Dog, 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 dog is our equivalent of 0 in this base 3 4-bit representation. Dog, 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 cat is our representation of 1, which occurs 4 times. Dog, 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 bear is the representation of 2, which occurs 10 times, and so on. So this seems to be working. Let's set symbolic to false, and this will give us keys as decimal, and it'll also give us our counts as decimals. So we could extend this further and give ourselves all of this information back in the symbolic form, but I don't think that's that helpful in terms of looking at this and analyzing it. So now that we have something that works for a symbolic system, we can kind of extend this idea a little bit to a brute force version of permutations. So let's consider this base count first, and let's get a dictionary of the base count, and our numeric system is going to be I'll just do this on another line. It is going to be the range. Let's go from 0 to, let's just do 0 to 10. And we'll think about the arrangements of let's do 5 numbers. And we'll just get all the permutations of this. So I'll go ahead and do this really quick, get adder, do symbolic distribution. And in D, we're looking for permutations. So we can think about a permutation as being a reduction from a series of numbers. And why don't we kind of walk through this a little bit? So we're just going to print this, and then we'll go from there. And just so you know, there are better algorithms than what I'm about to do, but this is a nice intuitive way to get at the idea of permutations. Okay, so looking at this, when we think about a permutation, we want to think about having unique numbers, okay? And so 99982 is not a permutation. In fact, none of these 999s, we'd have to get down to some, I'd have to scroll quite a bit to eliminate values in here that are not permutations. So when we're thinking about a permutation, let's just think about it in terms of being a rearrangement of the numbers that are there. So maybe what we can do is just write a permutations function, and I'm going to write it in here and then I'll move it up. So let's write permutations of some dictionary, and these are going to be the values in that dictionary. Is that how we want to do it? I think it is. I think this works. So let's do this. So permutations, I'm actually going to change the number of places here to 4 just to make it a little bit faster. So in permutations, we're going to get, let's just get all our counts out of here. Let's say this is d.values. And let's say for value in counts, let's remove all lists that have repeated numbers. And maybe we can do this as such. We'll just do it with a nested loop here. So for number in value, if value.count of the number is greater than 1, then we'll just break. And otherwise, we're going to append to our perms. So let's do that. Perms.append, and let's append the value. So let's return perms, and let's print, let's say for perm in, so perms is going to get permutations of d, which is above. And I'm going to go ahead and comment out this print statement here. And we'll say for perm in perms, why don't we just print the perm. Let's see if that works. Interesting. Seem to be something here that I'm doing wrong. Okay. Clearly. All right, so counts gets d.values, perms gets that. For value in counts, for number in value, if the number occurs more than once. Oh. Yeah. That's why that's happening. So let's just set a flag, and we'll set this flag to so we'll set perm to true, and we'll set perm to false if the number occurs more than once, and then we'll break, and then we'll say if perm, then perms.append value, and that should get us where we want to be. Yeah, and so here we've got permutations: 9876, 9875, 9874, 73, 72, 71, 70, 67, 65, and this is this works. Now maybe what we can do here is we could sort this value. And this might give us some other insight into what's happening here with a permutation. Let's do reverse. It's true. Okay. So 9876, 65, 75, 74, 73, 72, 71, 70, 9876. Why does that occur twice? We also need to check for duplicates here. So why don't we do that? If perm is true and perm not in perms. Okay. And perm. Oh. And value not in perms. There we go. So 9876, 75, 65, 74, 64, 54, 73, 63. And this, maybe we can also sort these permutations to go from lowest to highest. We're still getting duplicates in there. So 9876. 76. Interesting. Perm equals true if it is a perm and the value. I need to do this. Okay. A little bit ugly there, but because I was sorting it, it kept saying that those weren't in there yet. Okay. All right. So 9876 down to 9870, 9865. So notice we're skipping some. 9864, 9860, 9854, 9853. And we start seeing kind of a cleaner pattern here. And this form of permutations should be fairly intuitive. And we can also print the length of the permutations. So we can see how many permutations there are, actually. So the length of the perms. And it looks like there's 210. So what we can do is we can throw a different numeric system in here. And we can do, let's do just this dog, cat, bear again. And this should work for us. Oh. Let's see, for value counts. For, interesting. Do you want this to work arbitrarily? Okay, so getting the base count, passing a numeric system, and 4 places of that numeric system. Let's see what's going on here. Okay. So counts, gets, devalues, perms, value and counts. if the value dot count of the number, nope, that's good. I'm a little bit stumped here. Let's make sure that we're getting what we want out of this. So for key value in d.items, let's print the key and the value. That seems to be working, so and this always happens in live coding. All right. So for value and counts, perm gets true. For number in value, let's print the value. Okay. So that should be working. Still not seeing it. All right. Oh. Oh, yeah. I'm silly here. Okay. There's only 3 options here, and I'm trying to do 4 places. And that's just not really doable. Let's do a couple more animals in here. So let's do elephant, and let's do pig. It's actually a logical error, not the error that I thought it was. So the different 4-place permutations of this are elephant, dog, cat, bear, pig, dog, cat, bear, pig, elephant, cat, bear, pig, elephant, dog, bear, pig, elephant, dog, cat. So, okay, so that looks like it is working. And so this is just sort of like a, it's not a full permutations function. We're just rearranging, and that's that's fine for what we're doing here. So let's do let's modify this a little bit. Let's do a number of places, and let's do for value in counts, perm gets true. For number in the range of places, then I have to think about that. For number and value, we have to do well, I'd have to build a new list in there, and I'm not going to do that right now. Let's just leave this as very simple permutations of the same length as before. And I'm going to just grab this. Just don't want to run out of time. And let's just call this simple permutations. And let's make a note. This is just permutations of the length of the current length of the counting system. And I'll do that. And I think we'll leave it at that, actually. I think this is a good stopping point. And I said permutations here. My bad. This is actually combinations. And we did pass through permutations on our way here, but because in essence order doesn't matter anymore, and we don't have repeats, this is combinations where we ended up, not permutations. But at any rate, this should give you a pretty round idea about counting in general and how we can go from counting to things like permutations and combinations, and how we can build simple distributions in this way. So yeah, I think we're probably going to do a couple more of these kind of raw coding, approaches, given the current timeline at Galvanize, since we have another data science cohort starting soon. And then we'll probably start playing around with some, just something fun, some digital image processing, or something a little bit less kind of like in the code, and that we can look at a little bit more. So yeah, my name's Tovio Roberts, and I'll see y'all next Thursday.